Alright, so let's recall that we had these formulas last time. Formula number 1 was, if I take the sum of the first n positive integers, then the sum is given by n times n plus 1 over 2. If I add the squares of the first n positive integers, then I get n times n plus 1, 2n plus 1 over 6. If I add the cubes of the first n positive integers, we get n times n plus 1 over 2 squared. Notice that the right-hand side in number 3 is the square of the right-hand side of number 1. Alright, so what I want to do is use these formulas now to do some exercises. So let's say I have the sum I going from 1 up to 10, 2i squared plus I plus 1. Okay, so 2i squared plus I plus 1, that's the formula for the ith summand. One way to do this problem would be that you compute each summand and then add them. However, we want to use those formulas. So imagine instead of 10, I have 100. Then you wouldn't want to compute each summand and then add. Let's apply the formulas. So remember, one of the properties of there are two properties of this summation notation, and if I apply them, I get that this is 2 times the sum I going from 1 up to 10 of I squared plus the sum I going from 1 up to 10 of I plus the sum I going from 1 up to 10 of 1. So we can say that the given sum is equal to these three, the sum of these three sums, and then we can apply the formula here. What's the sum of the I squared? I going from 1 to 10. Well, in this case, n is 10. So in my formula, we're going to plug in n equals to 10. So remember that is n times n plus 1 times 2n plus 1 divided by 6. And for the sum of I, it is n times n plus 1 divided by 2. And the sum of 1, it means that you are adding 1 10 times, so you get 10. Okay, so what is that? 2 and 6 reduces to a 3 in the denominator. Notice that I have it, well, what do I have here? I have 10 times 11 times 21 over 3. And this would be 5 here, and 5 times 11 would be 55 plus a 10. And 3 and 21 reduces to 7. So what do I have? 770 plus 55 plus 10, which is equal to what? Which is equal to what? 780, 835. Is that right? Is everybody okay with that? Everybody's okay? Alright, so that's how we can use those formulas to compute some of these sums. Any questions? Any questions at all? Another example. This is a simpler one. Let's say I am adding the first 50 positive integers. First 50 positive integers. So by our formula, this is what? 50 times 50 plus 1 divided by 2, right? Is everybody okay with that? All right, so I'll let you simplify that. Everybody feels comfortable with summation notation. All right. What I want to look at next is the concept of partition of a closed bounded interval. So we are going to speak about partitions now. By a partition of a closed bounded interval AB, we mean a finite set of points P. So P here represents a finite set of points x0, x1, x2, xn. How many points do I have there? It's n plus 1, because between x1 and xn you have n of them, and then you have x0. So you have n plus 1 points here, such that remember, we are looking at the interval from A to B. The left end point of that interval A is always the first partition point x0, and then this is strictly less than x1, it is less than x2, less than ... At some point you have some partition point xi minus 1 and xi ... The second to last partition point is xn minus 1, and that's less than the last one, xn, and xn is the right end point of that interval. Okay? So we are basically picking a finite number of points in that interval, and we are calling that including the end points of the interval. So a partition of the interval from A to B always includes the endpoints of the interval. So let's look at a picture of what a partition does. So let's look at this. Let's say this represents the interval from A to B on the number line. So here's A and here is B. Remember, A is always the first partition point x0, and then I have the partition point x1, and x2, it would be on the right side of x1 because x2 is bigger than x1, so x2 would be on the right side of x1. So you keep going, and at some point you'll have some xi minus 1 and xi, and then you keep going again until you get the last one, which is xn minus 1, and remember B is xn. Okay, so you're picking a finite number of partition points. Why am I using the 2 points xi minus 1 and xi? If I want to So suppose that I want to make a general statement about the class, or about the students in the class. Okay, I want to make a general statement. So let's say that I have student number 1, student number 2. So everybody has a rank: number 1, number 2, 3, 4, 5, and so on. And if I want to say something about that applies to every student, right? I could say student number I has the following property, or whatever. Okay, student number I. So when I say something like student number I has this, that means I could be anything, any number between 1 and, let's say I have 50 students, between 1 and 50. So I'm trying to make a general statement about all the students from 1 up to 50. So I am saying student number I has the following properties, and so I don't have to say student 1 has this property, student 2 has this property. I can just say student I has this property, and that says that all the students have that same property. Am I making sense? So that's why I'm using this notation xi and xi minus 1, so that I can talk about all these points in a general statement. I can make general statements about these points. Now, what you want to notice here is that these partition points, remember we are using P to denote this partition, and what you want to notice here is that these partition points divide the interval into subintervals. These partition points has divided the interval from A to B into subintervals. How many subintervals do I have here? How many subintervals do I have here? So let's do some mental check. If suppose I have the interval from A to B, and I have only four partition points. So one of them would be A, the other one would be B, and there are 2 interior partition points, right? Realize that if I have 4 partition points, one of them would be A, and one of them would be B, and there will be 2 more inside that interval, right? If I have 4 partition points, how many subintervals do I get? 3. Right? Write it down. If you just write it down, you'll see that, for example, if I write it down like this, so here's my A, let's say, and B here, and then I pick 2 more partition points here, right? So I pick 2 more partition points here, then I get 3 subintervals. Am I making sense? So if I have 4 partition points, I have 3 subintervals. If I have 5 partition points, how many subintervals do I get? 4 of them. So how many partition points do I have when I use n? I have n plus 1 partition points, right? x1 up to xn plus x0, so there are n plus 1 partition points. So how many subintervals should I be getting? I should be getting n subintervals, right? The number of subintervals here, the number of subintervals is exactly n. You guys realize that? If I have 5 partition points, I have 4 subintervals. If I have 10 partition points, then I have 9 subintervals. Always 1 less. The number of subintervals is 1 less than the number of partition points. Is everybody okay with that? And we are going to call this n. The size of the partition. This is the size of the partition P. We're going to call n to be so what is the size? The size is the number of subintervals, or you can say 1 less than the number of partition points. That's the size. We also have this concept of mesh. So what's the mesh? The mesh of the partition is denoted by this symbol here. And by mesh, what do we mean? We mean, look at the lengths of all these subintervals. Look at the lengths of all these subintervals and pick the largest one. So that's the mesh of the partition. So let me write that down. This is the largest. This is the largest of the lengths. Largest of the lengths of the subintervals. Is everybody clear on that definition? Well, let's make these concepts clear through some examples. Let's look at example, and let's say we are speaking about the interval from 2 to 5. So A is 2 and B is 5. And let's pick a partition P1. So the partition P1, I am going to pick only 4 points, okay? Again, partition means it's a collection of finite number of points from that interval, including the endpoints. So you have to pick 2, you have to pick 5, and then you pick some others from the interval. Let's say I pick 3 and 4 and 5. So this is it. This is my partition. So in this case, what are the subintervals? What are the subintervals here? Well, I get 2, 3, 4, 5. So these are the subintervals that I get. How many subintervals? 3. So what's the size of this partition P1? The size is 3. The number of partition points minus 1, or the number of subintervals. What's the mesh? Mesh is the largest of the lengths of the subintervals. In this case, each subinterval has length 1, so the largest would be 1. So that's the mesh. Is everybody okay with that? Let's pick a different partition. Let's pick P2 to be the partition 2, 2.5, 3 for the same interval, 3.2, 3.2, and then 4.6, and of course, remember, you always have to pick 2 and 5 because these are the end points of the interval. So then, in picture, well, how does it look like? Well, here is 2, let's say, and here is, let's say, 2.5, 3, and this would be 3.5 and 4 would be right here, 4.5, and let's say 5 is here. This is 4.6, let's say. Let's say this is 3.2. Okay, so I get the partition points 2, 2.5, 3, 3.2, 4, 4.6, and 5, right? Okay, can someone tell me what's the size of this partition? The size of this partition, you're right, it is 6, because how many subintervals do I have? 6. How many partition points do I have? 7. 7 minus 1 is 6. And what's the mesh here? The mesh is? So look at the first subinterval. The first subinterval has length 0.5. The second one has length 0.5. The third one has length 0.2. The fourth one has length 0.8. The next one has 0.6. And the next one has 0.4, right? So the largest is 0.8. So that's the largest of the lengths of the subintervals, and that's the mesh. Okay, partition making sense to you? Okay, now let's do a little bit more trickier example. Let's say I am looking at the interval from 0 to 1, and now I'm going to ask a reversed question. So I want to pick a partition P. I want to pick a partition P such that the size of the partition P is n, where n is a positive integer. And I also want the following. I also want the length of each subinterval. I want all the subintervals to have the same length. Am I making sense? I also want all subintervals are required to have the same length. Okay? What my question is, can you come up with the partition points? So let's see if you can come up with the partition points. Again, the partition is required to have size n, and all the subintervals must have the same length. And our job is to come up with the partition points. Okay, so here is let's say the interval from 0 to 1 on the number line. Okay, and you tell me what are the partition points. One thing is clear: 0 is always the left-hand point. That's always a partition point, right? So this is my x0, right? So can someone tell me what should be x1? What would be the next partition point? What is the next partition point? Let me ask you this: how many subintervals would I have? I have n subintervals, and what's the total length of the interval? 1. All the subintervals must have length what? They have the same length, so each one has length what? 1 over n. The total length is 1. I have n subintervals with the same length, so the length of each subinterval would be 1 divided by n, right? For example, if I divide the interval from 0 to 1 into 3 subintervals having the same length, what would be the length of each subinterval? 1/3, right? You guys agree with that? So that is what I'm saying is, suppose that I am looking at the interval from 0 to 1, and I want to divide it into 3 subintervals having the same length. So that is, wouldn't you say this is 1/3 and 2/3? That is, if I divide it into 3 subintervals having the same length, then what's the length of each subinterval? It's got to be 1/3, right? The total length is 1. I have 3 subintervals having the same length, then the length of each subinterval would be 1/3, right? Okay, so then I want to do the same thing in general. What would be my first partition point? I want the length of the first subinterval to be what? 1 over n, right? So what should be this number, x1? In terms of n? 1 over n, right? Because if this point is 1 over n, then the length is exactly 1 over n, right? 1 over n minus 0, that's 1 over n. That's the length of the first subinterval. All right, someone tell me what's this third partition point? It'll be 2 over n, right? It'll be 2 times 1 over n, or 2 over n, because you want the length of the second subinterval. What's the length of the second subinterval? 2 over n minus 1 over n, which is exactly 1 over n. That's what you want. What is the maybe we should do one more here. What is x3? 3 times 1 over n or 3 over n. Okay, dot dot dot. So first interval, second interval, third interval, right? Let's say I'm talking about the ith subinterval. So this is ith subinterval is xi minus 1 and xi. That's the ith subinterval. Remember, the first subinterval goes from 0 to 1, right? 0 to x1. x0 to x1, that's the first subinterval. x1 up to x2, that's the second subinterval. The second subinterval and the right endpoint x2, right? They go together. Right? The index for the right endpoint tells you the interval number, right? So the index for the first subinterval, right? This index tells you the interval number. This index tells you the interval number. This index 3 tells you the interval number. So for xi minus 1 up to xi, that's interval number I. And what is xi minus 1? Yeah, it is n minus 1. No, not n minus 1, sorry. Well, look at x2, right? What is x2? 2 times 1 over n. x3, 3 times 1 over n. So xi minus 1 would be, I minus 1 over n. And this one would be I over n, right? And I have dot 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 again. And the last subinterval, which is xn minus 1, and this would be xn. Xn is of course 1, right? Which is what? N times 1 over n, right? Or n over n. And what's the second last one? Second last one would be n minus 1 over n, right? You guys agree with that? Is everybody okay with that? Well, let's pick another interval, and we want to do the same thing but with another interval, and it's going to change the problem quite a bit. So let's say I have the interval from 2 to 5. This time I am looking for a partition where the size of the partition, I want the size of the partition to be n again. Okay, I want n subintervals again. However, I am now requiring that all the subintervals have the same length again. So all subintervals have the same length. Now, what's the length of each subinterval? What's the mesh? What would be the mesh in this case? I am dividing the interval from 2 to 5 into n subintervals having the same length, right? So what's the length of each subinterval? The length of each subinterval is? What's the total length? What's the length of the interval? 3. And I want to distribute that length 3 into n subintervals, right? So the length of each one is 3 divided by n, right? 3 divided by n. Total length divided by number of subintervals. So I want the length of each subinterval to be 3 divided by n. Is everybody okay with that? The total length of the interval is 3, and I want to distribute that length among n subintervals. So the length of each subinterval would be 3 over n. And let's come up with the partition points. Okay, so here's my number 2, and 2 is x0, right? And what would be the next partition point, x1? What would you say? Was that? Is it just 3 over n? You have to add 2 to it, right? 2 plus 3 over n. So now look at the length of that subinterval. If you subtract x0 from x1, do I get 3 over n? I do get 3 over n, right? So the length of that subinterval is exactly 3 over n. What would be the next one? x2. What would be the next one? It will be again 2 plus what? Yeah, 2 times 3 over n or 6 over n, right? Twice the length, right? Twice the length. It will be twice the length away from 2, right? What would be the next one? Well, let me not do the next one. Let me just directly go to the ith one. So what is xi minus 1 and what is xi? What would be xi minus 1? It will be 2 plus I minus 1 times 3 over n. This one would be 2 plus I times 3 over n. Okay, dot dot dot. And I have the last one here is xn minus 1. And xn minus 1 would be 2 plus n minus 1 times 1 over n. And yeah, 3 over n, sorry, yes. 3 over n. And the last one is xn, and that will be what? That will be exactly 5. Okay, but 5 can be written, notice that, how do I know I didn't make a mistake? But because I know that 5 is the same as what? 2 plus n times 3 over n, and that matches with 5. So I know that I didn't make a mistake. Okay, so that's how I can come up with the partition points for this interval with the given requirements. Is everybody okay with that? Everybody's okay? All right. So why did we talk about partitions? Because now we are going to speak about Riemann sums, and we are slowly trying to develop the idea of definite integrals. Let me ask you this: given an interval, how many different partitions can you come up with? Given an interval, how many different partitions can you come up with? Infinitely many. Just pick any number of points, right? You get a partition, right? So you can pick a partition with 5 points, 2 points. You can pick a partition with 10 points. You can pick a partition with 1 billion points, right? 1 trillion points, right? So there are infinitely many partitions for the same interval. All right, next what I want to do is define what we call Riemann sums. So what are Riemann sums? So here I am going to take let f be let f be a bounded function defined on the interval from a to b. So f is a bounded function defined on the interval from a to b. What do I mean by bounded? What do you think I mean by bounded? When I say that the function f is a bounded function, that is there exists m and capital M, two numbers, such that the value of the function must be between lowercase m and capital M for all x in that interval. Am I making sense? So when I say I have a bounded function, it means that the values of the function are between two constants. The values of the function, all the values of the function are between two constants. That's what it means to say that the function is a bounded function. That is, there is a upper bound for the function, that the function cannot exceed that number. There is a lower bound for the function, meaning that the function cannot go below that number as well. So graphically speaking, if you look at the graph of the function lies between m and capital M. The graph lies between m and capital M. The height of the graph is between m and capital M. Am I making sense? So that's what we mean by a bounded function. Okay, so once I have a function like this on a given interval from a to b, I will be defining. I will take an arbitrary partition P. So a partition P. Let me just write it in terms of on the number line. So let's say this is our interval from a to b, and we have a partition with n points. A is x0, and then I have x1, x2, x3, xi minus 1 and xi, xn minus 1. Again, x0 to x1, that's the first subinterval. x1 up to x2, that's the second subinterval, and so on. And xi minus 1 to xi, that's the ith subinterval. Okay? And then the last one would be xn minus 1 up to xn. And so I'm picking an arbitrary partition of this interval. Now this is what I'm going to do. I am going to pick 1 point in each subinterval. I will pick 1 point in each subinterval, and this will be called sample points. So now I'm going to pick a point in each, let me use red, a point in each subinterval. So I'm going to pick W1 in subinterval number 1. I'm going to pick W2 in subinterval number 2. I am going to pick W3 in subinterval number 3. In the ith subinterval, I'm going to pick a point. I'm going to denote that by Wi. So the index tells you which subinterval it is coming from. And the last one I'm going to pick from the last subinterval. So in each subinterval, I am picking a point. And these are called sample points. Okay? So I am picking sample points. Sample points. W1, W2, Wn. Okay? And what am I doing here? Well, notice that the ith sample point is coming from the ith subinterval. Ith sample point is coming from the ith subinterval. Is everybody okay? Everybody is okay with that? Okay. And now I am going to tell you what I mean by a Riemann sum for the function f on this interval. What we are going to do is we are going to form a sum now. I am going to evaluate the function f at each of the sample points and multiply them by the corresponding length of the subinterval. So for the first subinterval, I am going to evaluate my function f at the sample point W1, And then I am going to multiply that by delta x1, where delta x1 means the length of the first subinterval, okay? Delta x1 is the length of the first subinterval. And then I am going to do the same thing for the next subinterval. I am going to evaluate the function f at the sample point W2 and multiply that by the length of the second subinterval. And I'm going to keep doing that. For the ith subinterval, I evaluate the function at the ith sample point and multiply that by the length of the ith subinterval. And I do the same thing for the last one, f of wn times delta xn. Again, what's the meaning of delta here? It means here delta xi means it's the length of the ith subinterval, right? It's the length of the ith subinterval. This is for all i's, right? I equals to 1 up to n. So these are the lengths of the subintervals. We are going to express this sum by using the summation notation, okay? So in summation notation, what is that? Summation notation, this is I going from 1 up to n. How many summands do I have here? I have n subintervals. For each subinterval I have a summand. So I have n summands. So I going from 1 up to n. And what's the formula for the ith summand? The formula for the ith summand is f of wi times delta xi. That's the formula for computing the ith summand. Okay? So I can express that sum by using the summation notation in this way. And this is what exactly we call, so this is what's called the Riemann sum. So this is called, this sum that we formed is called the Riemann sum of f on the interval from a to b with respect to the partition P. This is called the Riemann sum of f on that interval with respect to the given partition P. How many Riemann sums can I form for the same function, same interval? How many Riemann sums can I form? Infinitely many. It depends on what is the partition, right? For every given partition, I can form a Riemann sum, right? So there are many Riemann sums for the same function on the same interval, right? It varies over what partitions you pick, right? So, okay, so that's what it is. Let me very quickly do an example. And okay, so very quickly, one example. Let's say I have the function f of x equals to x squared, and I have the interval from -1 up to 1, and I am going to, let's say, divide the I am going to divide this interval -1 up to 1 into only two subintervals. So my partition P is very simple. There are 2 points in it, and in each subinterval I'm going to pick a point. So here I am going to pick the point W1 to be half. Here I'm going to pick the point W2 to be negative half here and a half here. Okay, and then what would be a Riemann sum here? The Riemann sum would be you evaluate the function f at negative half, and you multiply that by the length of the subinterval it's coming from, and the length of the subinterval is what? 1 plus f of half multiplied by the length of the subinterval 1, and then I just evaluate that. Well, what is f of negative half? That's 1/4 plus 1/4, which is half. So that's my Riemann sum for this function with respect to that partition. But of course, we want to pick bigger and bigger partitions, okay? All right, so I'm going to stop right here.